Hello, I am Nico from the University of Stuttgart and welcome to our talk about the ArchIBALD data integration platform bridging fragmented processes in the building industry. But first of all, what is the motivation behind our paper? Well, the demand for living space is increasing and is even expected to be almost doubled within the next 30 years. While 2015 the total building floor area was around 220 billion square meters, in 2050 it is expected to be around 415 billion square meters. However, the productivity of the industry has been quite stagnating in the past decades, while the overall economic productivity is increasing over the time. At the same time, the digitization of the construction industry has not really advanced. While there are already few opportunities and tools to digitalize data, the building industry still lags behind. And according to the McKinsey Global Institute Industry Digitization Index of 2015, the construction industry even ranks second to last, as you can see here in this picture. We believe that there is a high correlation of stagnating productivity and the low digitization index. Hence, there is a need for digital technologies to enhance the overall productivity. So, how does a typical modern building process pipeline look like? Well, first, during the computer-aided design phase, an architect designs a building with help of one of various softwares available. In this example, the goal is to construct a wood pavilion, hence we first design the pavilion itself. Then, during the computer-aided engineering phase, it is determined how the design can be realized by, for example, running simulations for structural analysis. After the engineering step has been completed, we can start with the manufacturing of single objects, with the help of several robots to speed up the process. In this example, you can see two KUKA KR robots which construct one cassette or plate for the pavilion. Finally, the on-site construction can take place. Over the past few years, new machines like the spider crane shown here have been developed which help to speed up the construction process. After all these steps have now been completed, we have finished the building process. The Buka wood pavilion depicted here is the resulting building. While single steps of the building process already use some new technologies, it still remains that currently the process is a one-way street, in which only a selected amount of data is shared across multiple phases. This leads to our contribution, which is to build up an information system architecture named ArchIBALD. For this system, we want to break the current one-way street of the building process pipeline, and we do this by integrating several feedback channels. Furthermore, we implement several domain-specific services for multiple layers of the general architecture. The ones we present in this paper work towards reaching the goal of our target application, which is the implementation of an automated, optimized task assignment and task schedule algorithm. Before we head to our target application, I first want to show the general ArchIBALD architecture. And we use the data lake architecture as a basis, based on the results of a study we conducted previously among expert researchers within the building industry. So, in the beginning, there are some data producers who do some local data processing and generate some data which is or can be relevant for ArchIBALD. Then, we want to ingest this raw data from heterogeneous sources into the data lake. At the data extraction level, this data is transformed into predetermined data models. These are dependent on the application they will be used for. Afterwards, we want to assess the data quality and possibly enrich the data if it is necessary. And then once the data has sufficient quality, data integration takes place and interconnects and unifies the data from different sources. The data offer a global perspective now, which will be leveraged by several applications. Also, we can gather some metadata in each layer. So now here you can see several services for each of the layers. And this is how a data flow between the services could look like. So services of a layer require data input from services from the lower layers, as you can see here. And also, as mentioned before, we also want to extend the typical one-way pipeline by integrating some feedback channels among several stages and services implemented. And now you can see the services we have already implemented and which will be presented now in the following slides and also in our paper, of course. So yeah, as I've mentioned, let's continue with the data processing for our target application. So in the first step, product data is produced by architects using various CAD software. For example, this can be the planned design of the wood pavilion shown previously, and this data then can typically also be translated to ISC, a widely used open standard. Furthermore, editors are used to describe available resources like machines and tools available for the manufacturing and construction of the building, and we use the standard automation ML for this. As seen here in step 3, we now want to extract the necessary information from the IFC and automation ML files. Then we want to assess the data quality of the extracted data and enrich it with help of several provided tools if it is necessary. After the data quality is sufficient, we can now match all the machines to the task they are able to fulfill. And then based on this, an optimizer tries to find the optimal task schedule based on a given optimization strategy. And as mentioned before, we have also implemented several feedback channels. And while we provide feedback when data quality is not sufficient and further data is required to be added, we also provide feedback if some task cannot be performed by any machine. So in the following, we want to explain the importance of the constant feedback. So first of all, if the data quality of our input is low, the feedback helps us guiding which data we or the data producers have to add in order to improve the quality of the application. And if one task cannot be matched to any resource, the feedback allows for an early adaptation of the approach, for example by changing the design or plan or by adding more powerful resources. So maybe the prefabricated wall is a little bit too big to be transported by the available transporters, so maybe we have to adapt the overall approach so that it is fabricated on-site or near-site. And these are typical challenges that often aren't thought of beforehand and come up during the process. So generally, early feedback allows for early adaptation, which reduces the amount of overall delays. Since the users want beforehand, the production can start with, for example, other tasks, while experts try to resolve remaining issues by, for example, adding resources. And as we have already mentioned, we use the widely used standard IFC to describe the design and tasks. and automation ML to describe machinery or resources. Here you can see the formal notation of the information we extract from these input files, but you can ignore the details. Overall, it contains data like the task and its corresponding objects, as well as specific object-related information. Then on the resource side, we save the resources along their skills and given limitations like limited operation space of the resources and so on. However, due to various reasons, relevant information is often left out. So we provide some tools which help in enriching the data. Often specific, more detailed information about an object's length, height, width, and volume is left out. So what our code does is that it can automatically generate this information by creating a bounding box over the geometry of an object. This information then will be automatically written back into the original IFC file. Furthermore, tasks are also typically not described in IFC, since architects focus on the design rather than on its realization. For this, a simple graphical tool has been developed, which lets users add IFC files and then add task-related information in a simple way. In general, the user will get feedback about all missing information, which are potentially relevant and which cannot be automatically generated. So this information then has to be added by the experts manually. If not, there are also available continue options, but the quality of the overall results could suffer. With the enriched data, we can now move on to the data integration level. And here we want to provide a matching algorithm that matches all machines to the tasks they can perform. So here you can see the design of a cassette of the wood pavilion shown earlier, which requires several tasks to be fully manufactured. We want to match available resources to each of these tasks if they are able to perform them. More precisely, since tasks may contain implicit subtasks, we have to match all subtasks to the machines. Basically, we perform several constraint checks, and if all constraints are fulfilled, the pair M and ST is flagged as a match, and an estimated duration is calculated as well. Since this would require more data and expertise, the duration is reasonably randomized currently, since this information is needed for the task scheduling step later on. Sometimes we have several machines assigned to implicit subtasks, so one complete task might require several machines. If several resources are able to perform a specific subtask, we end up with several possible machine combinations. Now, there are several special cases in the real world, which is why we have to prune some of the machine combinations. For example, a task might consist of the implicit subtask that you first grip one partly assembled object, like it can be seen in this picture, that the left robot arm grabs the cassette, then some other tasks are performed, and in the end the object is released again. In this case, the robot that grips the objects obviously also has to be the one which releases them. So that's why we have to prune all previously found machine combinations which have assigned a different robot to the grip task than to the corresponding release task. There's also a similar case in multi-step transportation tasks we have found. And if there is a task that cannot be matched to any resource, some feedback is then provided to the user. Based on the task assignments, we now want to find the most optimal one along with an optimal task schedule. Finding an optimal task schedule for fixed assignment of tasks is a well-known NP hard problem. Additionally, we consider multiple possible assignments up to m to the power of n, with m being the number of machines and n being the number of subtasks. Hence, we need a heuristic approach since an optimal solution is impractical. We don't go into detail of this approach, but generally we have two possible optimization strategies, one for optimizing the cost and another one for optimizing the overall time needed. The overall runtime complexity of this approach is T times M times N, with T being the number of overall tasks. In summary, we can say that we presented the general architecture of ArchIBALD, which introduces feedback channels to break the one-way street of current building processes. We furthermore showed some services of each layer we have implemented for our presented target application of task assignment and task scheduling. However, we still have lots of grey boxes left out, so future work is about implementing more services with different applications and goals in mind. Furthermore, the amount of data could and should be enhanced for more detailed matching constraint checking, for better output solutions, if a machine can really perform a task. The simple approach with the limited amount of data we had to work with might not be sufficient enough. For example, we checked if a machine could perform a task, but not where the machine is currently located and if it even can fit on the on-site construction, and so on. Also, further research to automatically give precise estimated time duration of a task is a potential future work which requires lots of expertise and more data. So that concludes my talk. Thanks for your attention, and I'll gladly answer any questions.